So let's take a look at some properties of alkenes and alkynes. And what you're going to see here is that they're pretty much the same as alkanes. The first thing is that they are, because they're all hydrogen, have only hydrogen and carbon in the molecules, they are nonpolar. Because if you look at them, they either have carbon-carbon bonds or carbon-hydrogen bonds and nothing else. Yeah, some of those carbon-carbon bonds are double bonded or triple bonded, but it's still a carbon-carbon bond any way you look at it. So they're all nonpolar because every bond in the molecule is nonpolar. What that means is that they are not soluble in water. And we already pretty much knew that. Once we learned that they're nonpolar, we already know that they're not soluble in water because, well, remember, nonpolar things don't mix with polar things. But polar things mix with polar things, and nonpolar things mix with nonpolar things. And so any alkene or alkyne, or alkane for that matter, is not soluble in water because water's polar, and all those molecules in those three families are all nonpolar. However, any alkene can mix with any alkyne or any alkane because any of them can mix because they're all nonpolar. And then the last thing to talk about is that they are flammable. So these guys burn just fine, and they're flammable just like alkanes were flammable. Just as a quick check of our understanding of some of these properties of alkenes and alkynes, we might have a question like this. Is 3-methyl-1-octene soluble in 3-no-9? This is nothing we need to memorize directly, because that would be a huge a grid of reactants and two reactants and trying to determine if they're soluble with each other to memorize. But really, we can just use our little clue here, and that is we can see that one of the molecules is an ene, means it's an alkene, and we know that alkenes are nonpolar. We can also see here an ine, and we also know that alkynes are nonpolar. And we also understand that nonpolar things mix with nonpolar things just fine. And so the answer to this would be yes, that these are soluble in each other because both molecules are nonpolar, because both families are nonpolar. And so that's the simplicity with these types of questions, these solubility questions, is that you just have to determine if they're polar or nonpolar. Now, one thing to know about reactions of alkenes and alkynes is that they love to target the carbon-carbon double bond of alkenes or the carbon-carbon triple bond of alkynes. So those reactions, when you see an alkene or alkyne, the main target is going to be those double and triple bonds. The reactions we're going to be talking about, and a lot of reactions that happen with alkenes and alkyne, are what's called addition reactions, are the most popular type, or the most common type, I should say, of reactions. And what an addition reaction is when you take one molecule, we'll call it A, and you take a second molecule and call it B, and you put them together to make a molecule AB. So we're going to combine two things together. Notice there's two in this example here. There's two reactants, A and B, and there's only one product because they were brought together to form a single molecule. And so be looking for these couple of things as we go through. So we're going to talk about 4 different reactions. The first one we're going to talk about is hydrogenation. Notice the word of these reactions kind of gives away what it does a little bit, at least gives you a clue. In this word, you see the word hydrogen. And what hydrogenation is going to add is a molecule of hydrogen. Now remember, hydrogen exists not as a single atom, but as 2 hydrogens connected. So there's a hydrogen that's going to be one of the reactants. And in this reaction, we can take any alkene or any alkyne. And so I'm going to make it very simple here. We're just going to take a simple alkene. I'm going to take the simplest one, and we're going to take ethane, or I'm sorry, ethene, and we're going to add a molecule of hydrogen. And what are the products going to be, or what's the product going to be? This is an addition reaction, because let me show you how this works. I'm just going to move this molecule of hydrogen. So I'm going to move it from where I have it in the reaction, just so I erased it. And we're going to move it down here where actually the reaction is going to occur. So all I've done is move that molecule. So there's our two molecules. We have alkene and we have hydrogen. And what we're going to do is we're going to put them together. And these reactions, again, love to go after that double bond and break that double bond. And so what's going to happen here is we're going to move one of these bonds, the one between the H and the H, and we're going to move it over to here. So I'm going to draw a new molecule bond there. And we're going to go ahead and erase the old bond. Now I'm going to erase my arrow as well. And then we're going to take the other bond here, one of these double bonds, and move it here. And draw the line in there. And now let me erase what was moved. And notice what we have here now. What we made here now was, and this is now our product, we have made alkane. An alkane, and this is ethane. Notice now there's no carbon-carbon double bond, so it's an ane, and it's got two carbons in it, it's eth, and so therefore there's ethane. And so what these guys do is these guys break those double bonds and triple bonds. If we repeated this reaction with ethine, and we're going to hydrogenate it, notice again, we set it up like this. We can see that there's going to be a carbon-carbon triple bond, and so we know that's very reactive, and so it's going to want to react. So once again, let's move our hydrogen molecule in position, and notice that when you do an addition reaction across an alkene or an alkyne, the molecule that's being added, one part of the molecule goes to one of the carbon atoms, and one molecule or part of the molecule goes to the other carbon atom involved in the double or triple bond. And so again, here we are. So we're going to move one of the bonds, the one between the hydrogen and hydrogen, over. And now let me get rid of the bond that was moved. And then we're going to go ahead and move one of the carbon-carbon triple bonds, just one of them, we can only move one, between the carbon and hydrogen. And let's get rid of that. And you can see here as our product, we get an alkene. And so we can see it's an alkene, and so we know it ends in ene, and we see there's two carbons, so it's ethene. And so now we've made the molecule ethene in this process. We could add, just as we saw in the previous example, we could add another hydrogen atom or hydrogen molecule to this ethene and make an ethane. And so with hydrogenation, what we do is we can take alkynes and convert them into alkanes or alkenes, and alkenes can be converted into alkanes, because each step of this process just keeps adding on hydrogen atoms across those triple and double bonds. And so hydrogenation is a great way to convert one family member into another family member, an alkyne into an alkene, as we just saw in this example, and an alkene into an alkane, as we saw in the previous example. So the second type of reaction we want to talk about is halogenation. We've seen halogenation before. We can see again the word gives away a little bit of what's going on here, halogens. And remember, halogens are things like Br2, chlorines, iodines, and fluorines are halogens. And remember, just like the hydrogen atom, Br2 is two bromines connected together by a single bond. So they share one bond with each other, share electrons to form a bond. And so, again, we can take any alkene or any alkyne and do what we basically did with the hydrogenation but now we're just not using two hydrogens, we're using two halogens in this reaction. So let's set one up. Now here we go. We have a halogenation reaction set up where we have an alkene, ethene, and we have bromine. And we're going to add those together. And again, it's going to look just like we did on the previous examples with hydrogens. Let me go ahead and move my halogen into position. Again, there's my halogen. We're going to go ahead and move the halogen bond, and we're going to go ahead and move one of the carbon double bonds over. Let me erase what we moved. And what we can see here now is we have now made an alkane, but this is a dibrominated alkane that we have made. So although we still convert in a halogenation reaction an alkene to an alkane, in this reaction though we've also halogenated the molecule as well. So we've done two things essentially to it. And so here what we've made is the molecule 1,2-dibromo ethane. So 1,2-dibromo ethane when we started with ethene. So that was a conversion. So this is a great way to not only change the family, but also to add halogens to the molecule. We could also do this with an alkyne, and in that case we'd convert an alkyne into an alkene and also halogenate it. You can use any halogen you want. You can use bromine, chlorine, iodine, or fluorine in this reaction, and they all will come out with a dibrominated or dihalogenated molecule. Now just to contrast this for just a second so we're not confused, in a halogenation reaction of an alkane, not an alkene and alkyne, which is what we're talking about in this lecture, but an alkane, in that, remember, it's not an addition reaction. We don't take both chlorines and add them to the alkane. We just take one of the chlorines and switch it with one of the hydrogens, so they switch positions. So in the alkane reaction, we weren't doing an addition reaction. We weren't adding two things together to make one thing. We were switching two things, and so in alkanes, when we halogenate them, that's called a substitution reaction, just to contrast it, so you can see some contrasting between what's an addition reaction versus what's a substitution reaction. So here would be a substitution reaction where we're just switching two things. So we have two reactants, shown here, the alkane and the chlorine, and then we'll get two products in the substitution reaction. The singly brominated or singly halogenated alkane and an acid. So we'll get two of each, two reactants and two products. So again, I'm just showing you this so you can see what's the difference between some of these different types of reactions. So we can, when I say an addition reaction, that means something to you versus when I say a substitution reaction. That's a little bit different. The third reaction is a hydrohalogenation. Again, we can look at the word and tell us a little bit. We see hydro and we see halogen. So we know what a halogen is, and hydro is just going to be an H. So we can be talking about HBr. It's a hydro. It's got a hydrogen and a halogen. Hydrohalogen. HI is a hydrohalogen, and HF is a hydrohalogen. And again, notice we have two atoms here, and we're going to be dealing with alkenes and alkynes, which love to have addition reactions. And so you can see what's going to happen here, or we can probably guess a little bit what's going to happen here, thinking about what reactions 1 and 2 did. So you can see that these reactions, these addition reactions with alkenes and alkynes, have very similar look to them. This time I'll go ahead and take an alkyne in this reaction. And so there's our reaction setup. We have an alkyne, which is ethine, and we have a hydrohalogen, which is hydrogen fluoride. So we're going to go ahead and add these two together. I'm going to move my hydrogen fluoride down to where we can kind of see how it's adding. So we'll move it right on down here. And we're going to do the same mechanism as we did before. I'm going to move this bond between the H and the F. I don't have to move it that way. I could move it to the other side. I'm just moving it to this side just because that's what I've been doing. So that one moves in that location. Let me get rid of that bond. And then we're going to go ahead and move one of these bonds. We're only moving one, not all three, not two of them, just one of them. So I'll move it to there. So let me get rid of the one I moved. And there we go. We have two new bonds there. And so we converted that alkyne into an alkene again. So again, we're seeing that again, that whole flow of breaking that triple bond down to a double bond or breaking the double bond down to a single bond. And in this case, instead of adding two hydrogens or adding two halogens, we added one hydrogen and one halogen. And so in this case, we're getting a singly halogenated molecule. Again, if we had another molecule of hydrogen fluoride, we could add it. And so let's go ahead and do that. Now there's actually two ways we could add it. We could add it. So I'm going to put it up here. We're going to go ahead and add it. We could add it like this. I can move that bond to there and move this bond to here, just like we've done before. Erase what was moved. And we can get that molecule. Now notice in this one, both fluorines wound up on the same carbon. They both wound up on this carbon right here. Notice that carbon has two fluorines on it. Let me show you something here. Wonder if, let's put it back to where it was. We had a carbon-carbon double bond. Let's go ahead and add the HF again, but this time, wonder if it showed up in that direction, which is fine. Notice still the hydrogen is still connected to the fluorine. It's just turned. And notice we can go ahead and drop one bond there, one bond there. Let's get rid of the bonds that moved. And notice in this one reaction, we get one fluorine on one carbon atom and one fluorine on the other carbon atom. Which one's the correct product? Is it this one or the previous one where the two fluorines were on the same carbon? It turns out both are made. And both are made probably in equal amounts typically. At least on an ethine, I should say. And so that's also possible as well. And so sometimes there can be multiple products because of the way in which they can add on. The last one I want to talk about is hydration reaction. Hydration sounds just like what it is. It sounds like water, and it is. And so water, of course, is H2O. And so there's water. Now this one you might be going, well, wait a minute, there's two bonds in here. And so which one is going to actually add across, and how's that going to be? In all the previous examples, we had two atoms, and so each atom of the molecule went to attach to the carbon. Well, in this one, it's actually going to break either bond. It can break this one or this one, but notice the answer is going to be the same no matter which one it breaks. If it breaks the one on the left here, you're going to get H, and you're going to get OH, right? If it breaks the other bond, so the one over here, you're going to get H and OH. So either way that it breaks, it doesn't matter. One thing that's going to add to the carbon is an H, and the other thing that's going to add to the other carbon is an OH. It doesn't matter. But notice the OH will wind up on different carbons depending on which one breaks. And we'll see that in just a moment. So let's set up a hydrogenation reaction. So here we have a reaction set up, and we have an alkene on the left, and we have a molecule of water. I'm going to move that molecule of water into position because it's still going to be an addition reaction. So even though the molecule here has 3 atoms instead of 2, it's still going to be the same idea. So there it is. I'm going to break that bond. Notice I really show it explicitly here. I show the bond. This one I'm not showing explicitly. It's there, but I'm just not going to show it because I'm going to clearly show which one I'm going to go ahead and break. So we're going to move again. We're going to move one bond to there. So I'll get rid of the one that moved now. And we have the other bond going to move here, which will actually fall between the carbon and oxygen, because remember, oxygen likes 2 bonds and hydrogen only likes 1, so that carbon is attached to the oxygen of the OH group, not the hydrogen. If attached to the hydrogen, hydrogen would have 2 bonds and it wouldn't like that at all. So that bond is from the carbon to the oxygen there. I can get rid of the bond that moved. And so again, we've converted an alkene into an alkane as our product. And we've attached an H to one carbon and an OH to the other carbon. And so in a hydration reaction, one thing that's binding to the carbon of the double or triple bond is a hydrogen, and the other thing's an OH group. Now, we could have had this add the opposite way, and I'll show you that. So this is one possibility where the OH ends up on the middle carbon in this molecule. Notice there's 3 carbons in the molecule, so this is a propane derivative. It looks a little bit, it has 3 carbons, so it's a prop. And you can see that the OH is attached to the middle carbon, but let's go ahead and change this. And notice, depending on how the H and OH showed up to this reaction, and they can do both ways, if it was set up like this, and we added this across the alkene, notice we move one bond here, and we move one bond here. And when we do that, notice it's a little bit different this time. Yes, we still added a hydrogen to one carbon and an OH to the other carbon, but this time the OH ended up on the first carbon as opposed to, whoops, I forgot to erase that, ended up on the first carbon instead of the second carbon. And so when you have these molecules, notice when we have these 4 addition reactions, one of them was HH. There's no orientation there, so no matter when you add that across the double or triple bond, each carbon is getting the same thing. One is getting a hydrogen and the other one is getting a hydrogen. When we did a halogenation reaction, notice it's the same as a hydrogenation reaction, where you have 2 bromines. One bromine is going to end up on one carbon, the other bromine is going to end up on the other carbon. So again, there's no orientation there. Each carbon is getting the exact same thing in both of those 2 reactions. In the last 2 reactions, notice one is getting a hydrogen and the other is getting a chlorine. In that one, each carbon is going to get something different, just like with water. And so with the last 2, you have to remember that there's a lot of times 2 potential products, because it could go on one way where the OH or the chlorine or whatever ends up on one carbon and the hydrogen ends up on the other, but it's also possible that it could flip, where the other carbon gets the hydrogen or the OH or the chlorine. So these 2, the last 2, don't have the same thing attaching to each carbon, which then gives rise to multiple products. Okay, so here's one for you to try. So what I would do is go ahead and pause the video, see if you can come up with the answer, and then we'll come back and we'll chat about it. So I'll go ahead and answer it now. And so what I'm going to do is I'm going to go ahead and move the water molecule and just move it down to where I can see it next to the double bond. You don't have to do this every time. It's just something I like to do and show as a way to learn it, and then after a while you might get more used to what the product would be. You won't have to do this necessarily, because you don't have to go through this step to actually get the answer. You can eventually see what you need to do. So I'm going to go ahead and do it this way, and I'm going to go ahead and add and move that bond there and move that bond there and erase the bonds that were moved. And so after it reacts, that's what we'll get. So we've added the water molecule to the alkene to make this alkane. And I can see here that I have some butene, where I have carbon 1, 2, 3, and 4. And then on the second carbon, there's this OH group. So we have something OH. We'll learn. This is an alcohol, but we'll just call that 2OH. Butane is what we made. That's the product. Now, because this is a symmetrical molecule, if you actually draw it the other way, because remember the OH could have wound up on the other carbon, and I'll just go ahead and draw that in there. This is the other way the OH could have ended up on there, just like that's the other possibility. So I'll go ahead and draw that one. But notice in this one, we would number it the other direction. 1, 2, 3, 4. So in this case, although it looks like it can go on two different ways, it's going to actually make the same molecule because this molecule is very symmetrical. So that was just an oddity of this molecule, but it would still make, even by the purple numbering, it's still this 2OH butane. Now, I'm not naming that correctly at all. That's not how you would name this molecule. That's something that's for more alcohol purposes, and when we start looking at alcohols, then we'll see how OHs and how OHs are named. But because we're not to alcohols yet, I'm just going to leave it like that. But in the end, notice it makes the same molecule. Now, that wouldn't be true if I had, let's say, something else on here. Let's say we just put on here, I don't know, a bromine. Now it would be different. Well, first of all, it wouldn't be a butane anymore. It'd be something else. But now notice, in this case, in the purple numbering, or the way I have it now, the OH would be on the middle carbon. The way I had it previously, now the OH would be on the carbon with the bromine, and so that would be two completely different molecules. So when you have, you're adding on something that has two different things adding on to those carbons, like in this case, you have to think about the two different directions it can go on. In this example, though, the original example I had for this problem, it wouldn't have mattered which way you put it on. You're really making the same molecule.